I'm from University of Southern California, and I'm going to present IPDC iterative part-based dense correspondence between point clouds. So the goal is to find dense correspondence between two point clouds. They can be different in source. For example, one is a real scan from a laser scanner, and the other is a synthetic scan from a CAD model. And ideally, if two objects have exactly the same geometry, then the problem is trivial, and we can just establish the correspondence by just simply a rigid transformation. But in practice, due to limited size of the object library, a perfect match does not always exist. So if we can only find the matching object of the same category, but with different geometry, then the dense correspondence becomes hard. And we need to make another assumption that the two shapes have the same set of subparts, but can be different in configuration and numbers of them. So in other words, they have the same atoms, but are different molecules. And application of this is color transfer. And here is a simple pipeline of our method. In the first place, we segment both point clouds to identify their subparts, and then we establish sort of the part level correspondence. Let's first discuss about segmentation. So what makes a subpart? Our observation is that it is a set of points connected in Euclidean space and also sharing similar geometric properties which can be characterized by local geometric descriptors. Which means if we embed the point clouds to a high-dimensional descriptor space, a subpart is likely to form a cluster in that space, and we can apply unsupervised clustering in this high-dimensional descriptor space. And this clustering process tends to oversegment the point cloud. That is why we do this boundary refinement. We also want to align the boundaries to shape features such as creases. And we formalize this problem as energy minimization. And after that, we do region growing to separate the individual subparts. Okay, after we identify the subparts for both shapes, we establish part-level correspondence. The goal of this step is to assign each target part a rigid transformation to align with the corresponding source part. Of course, the basic strategy is to find the most similar one for each individual part, if we assume that a similarity metric is already defined. However, this can be not robust. Of course, we have no problem finding correspondence for the hub and the rim, but for the spokes, they have multiple equivalent choices, and the matching process can be noise sensitive. And our solution is to add another criterion that is least rigid transformations, which means we encourage the subparts to be transformed together and to preserve the original placements as much as possible. And here is an example. Assume that we are going to find correspondence for the two letters with different number of runs. And we start with the largest target subpart, which is a red set rail. And then we rigidly register it with its most similar source subpart. And then we ask all other subparts if they can join. And if they can, they will be transformed together. And this process will be repeated, and in later iterations, the remaining subparts will be handled correctly. As a result, we can transfer color from a real scan of a letter to another synthetic letter with different number of runs, and also to a V-shaped letter with completely different geometry. And to quantitatively evaluate the algorithm, we treat the problem as a multi-label classification problem, which is a subproblem of the correspondence problem. And if a correspondence connects 2 points with the same label, we consider it correct. And we measure the overall accuracy of all the algorithms. And as shown in this table, all algorithm outperforms others in most test cases. And for more details, you're welcome to the poster session. Thank you.